Okay, good morning. So it's a little bit cold outside, right? I think today is the last day actually, right? Anyway, so today I'm going to finish chapter 2, I guess, right? So this chapter will be done. Just few things are left. And after that, we in the next class we are going to start block cipher. You will see the beauty of block cipher. And of course, you know, that portion normally people don't cover in the first cryptography class. Some of the analysis, but we will do that. So anyway, so today also I think so. The main thing is that even if you don't understand the proof in one go, it's okay. So you should try to guess the sense. What we are trying to do, and then maybe sometimes when you go over it again and again, then you can find you can understand it better. One more thing that for most of the analysis part in crypto systems, as you will see that we heavily depend on the statistical properties of the language. Okay, so for example, English we are using here, and as I mentioned that for other languages, of course, I'm not aware of the literature. I have not seen that, but maybe it will be a nice thing to look at it. Anyway, so we talked about discrete random variable. We talked about joint probability, conditional probability, independent random variable, Bayes theorem. We talked about perfect secrecy, and this the definition, one theorem, and also we talked about the characterization of perfect secrecy. Okay. Then we talked about entropy of random variable, and as you know that plain text, ciphertext, and the key can be look at as a we can look at them as a random variable. So we can talk about their entropies. So this is the definition of entropy of a random variable. So we can talk about HK, HP, HC. Okay, entropy of key space, plain text, and ciphertext. And we have given examples. We talked about Jensen's inequality, which is useful for computing different entropies. Okay, and we also have entropy of x comma y. So x and y are random variables. X comma y you can think of a vector basically. So you can again define in the same manner as h of x. Okay, we can think of it as a vector. So anyway, this entropy of x comma y is less than or equal to h of x plus h of y, with equality if and only if x and y are independent random variables. The proof was straightforward. So of course we have not. I mean, it's a very straightforward thing. So we go the next thing. Now I'm going to talk about conditional entropy. So what is conditional entropy? So if x and y are in random variables, and suppose fix y to be a member of y, then x bar condition y is a random variable here in this case. Then entropy of such variable is, I mean, the definition is precisely the same. Okay, just like that, where x, the summation runs over x. Okay, so motivated from there, we can define conditional entropy h of x condition y. Again, you can see that here there is a double summation. It's a kind of weighted average with respect to probability of y. Okay, so the whole thing is probability of y times probability of x condition y times log 2 base probability of x condition y, right? So this is the definition of conditional entropy. Now, once we defined for two random variables x and y conditional entropy, we can talk about, and of course, there is a relationship like this joint entropy h of x comma y is same thing as h of y plus h of x condition y. All these, some of these results are given in the book Elements of Information Theory by Thomas Cover. So that's a very decent book. Each computer science student should have that copy in your office anyway. And the corollary to this is that h of x condition y is less than or equal to h of x with equality if and only if x and y are independent random variables. So these are just relationship. One can prove these things by evaluating the summation and so on. Anyway, now we talk about our crypto system. So, and conditional entropy of k condition c. So k is the random variable for key and c is the random variable for the ciphertext. So this conditional entropy is nothing but the amount of uncertainty of the key remaining when the ciphertext is known. Okay, so this is kind of the measurement this entropy does. Okay, and again, so if P, C, K, E, D is a crypto system, uh, we have a formula to compute it. One can compute it directly using the arguments. One can do the direct arguments as well, but here is a formula that H of the entropy of K condition C is entropy of K plus entropy of P minus entropy of C. So proof is again based on certain observations. First observation, that entropy of KPC, so K is random variable for key, P is random variable for plain text, C is random variable for ciphertext. You can observe that this is nothing but H of entropy of C condition K comma P plus H of KP. Okay. Now, key and plain text determine the ciphertext only via this relationship y is equal to ek of x. So this value is 0 as CKP is 0. So we are left with HKPC is equal to HKP. Okay. And since K and P are independent random variables, HKP is nothing but HK plus HP again from the formula, right? So HKPC is equal to HK plus HP. This is one relationship between, Now we will observe another thing. So this is just one equation to keep in mind. Now since there is a unique way you can decrypt, so we also have HPKC is equal to 0. So that means HKPC is equal to HKC. And now HKC is nothing but, a minute. So H of K condition, so K condition C is nothing but HKC minus H of C. And again, I'm using this because in the previous relationship, HKC is equal to HKPC, right? So we can just use this here. And HKPC is equal to HK plus HP from the previous relation here, this one. So we arrive at this formula. Okay. So our formula is, if you want to compute the condition entropy H of K condition C, it is you compute the entropy of K plus entropy of P minus entropy of C. Now I'll show you with an example actually how this works out. So let us see this example. This example is what we have computed earlier. HP of, suppose HP is 0.81, HK is 1.5, HC is 1.85. Then from this formula you can compute HK of C is equal to 1.5 plus 0.81 minus 1.85, which is around 0.46. And one can do it directly. This example I'm taking what we have done earlier. Okay, so we can compute these things directly and arrive at, so this is one way of getting it. Another way is that we can arrive at this calculation directly, so it is, you see, you can check that it is again 0.46. Okay, so this is all about entropy. So if you use this formula, it is easy for you to get the answer for the condition entropy, right? Okay, so next topic is about spurious keys. What are these spurious keys? I will actually find a bound on these keys. So suppose we have P, C, K, E, D, our crypto system. Plain text is x1, x2, xn. Ciphertext is y1, y2, yn. Okay. So basically, suppose ciphertext is given to you, right? And when you try to decrypt the system, you may get some meaningful keys. Sometime there are a couple of meaningful keys. I'll give you an example actually, and one of them is correct, and other may not be correct. So look at this. Suppose ciphertext is WNAJW, and we are assuming we are working with shift cipher. So meaningful, things are meaningful. Plain text is coming like river or arena, right? And here the key F is equal to 5, and here the key W is equal to 22. Now these two keys, one of the key is correct, other one is spurious key, right? So basically, out of available keys that you will look at, right, we want to find out how many such keys are there. Okay, spurious keys in given a ciphertext. This is something, important thing to calculate. We will give you a bound on such keys, and in order to calculate a bound, I need to look at some properties of English language, or in fact, we need to define entropy of a natural language. So this is something I'm going to build the ideas slowly. Okay, so suppose L is our natural language. So again, as I mentioned, for English, we have assumed certain things. For other languages, you can try in similar way. Of course, that is kind of. So suppose L is a natural language. The entropy of L is defined by HL. This means the average information per letter in a meaningful string of plain text. Okay, entropy of a natural language. A random string of alphabetic characters. Entropy in English is actually, if there is a random string, is log 2 base 26, which is around 4.70. Okay, in the random. Now, if L is a English language, entropy of P is again using Piper table. The table of the things that we have shown you earlier. This turns out to be close to 4.19. Okay, if L is a English language, this entropy turns out to be 4.19. So now I think we can get better approximation if we take diagram or trigram. For second order approximation, so probability distribution of diagrams divided by 2 is our value, right, for this entropy. So in general, we can look at if Pn denotes a random variable for all n grams of plain text. L is in our natural language. Then entropy we can define as limit n tends to infinity, entropy of Pn divided by n. Okay. So what is Pn? The random variable for all the n grams of plain text. So this is the definition that we are going to use for the entropy of language. And redundancy of L is defined as 1 minus HL divided by log 2 base P. Now redundancy is something very, obviously now for English language I should say that HL turns out to be between 1 and 1.15. So if we take some number of HL, I can find out how much redundancy is into the language. So it turns out that for different approximations, so basically for English language, HP square divided by 2 is 3.90. HL is between 1 and 1.5. So if you take HL is equal to 1.25, then it turns out this value is basically 0.75. So that means every English language is 75% redundant. If HL is between is between 1 and 1.5, means if it is 1.25 actually. Okay, so this is a kind of a rough estimate how much redundancy is there into the system. Okay, so now we can just try to finish this bound. So we need to define few terms. So K bar and Pn are our random variables, right? Pn is for that n grams, and K is for random variable for key. So induced probability distribution on Cn is a set of all n grams of ciphertext. So Pn is a random variable for n-gram of plain text. Cn is a random variable of n-gram of ciphertext. Now, if I take y in Cn and define k of y as all those keys in k bar, such that there exists x in Pn, such that probability of x is positive. Okay, and encryption of x will give you y. So this is nothing but set of possible keys given that y is a ciphertext. So if ciphertext is given, what are the possible keys is defined by this. So I can actually compute the size of this set. Okay, so if y is observed string of ciphertext, number of spurious keys is basically size of this set minus 1, because one of them is correct key, right? So we need to avoid the correct key. Total size will be this, right? Size of ky minus 1. So the average number of spurious keys over all possible ciphertext strings of length n is given by this formula, right? Sn bar is equal to summation y in Cn, probability of y times ky minus 1, size of ky minus 1. This is the average, right? Number of spurious keys, right? Now I can simplify this. I can open the summation, and then we know that summation y in Cn, probability of y will be 1, right? So here we have Sn is equal to summation y is equal to Cn, probability of y ky minus summation of probability of y in Cn. This quantity is 1. So Sn turns out to be summation y in Cn, probability of y times size of ky minus 1, right? Now again we have this observation, the entropy of k condition Cn is equal to entropy of k plus entropy of Pn minus entropy of Cn, right? So now entropy of Pn is approximately n times HL, okay, which is, I can use the definition of HL. So this is n times 1 minus RL times log 2 base P, and so that means H of Cn cannot exceed n times log 2 of C for large n. I think we can simplify it further. So if size of C is equal to size of P, then entropy of K condition Cn is at least Hk minus n times RL log 2 base P. So now I can actually, if I go by the definition, H of K Cn is this, right? This I can open, and actually, so this is summation. By Jensen's inequality, I mean, this is less than or equal to probability of y in Cn log 2 base, size of ky. Here we have used, Jensen's inequalities. This whole thing is less than or equal to log 2 base this quantity. So which is, log 2 base Sn plus 1. Okay, I'm using the formula from the previous one. So basically, we are left with this definition, this bound here. H of k Cn is less than or equal to log 2 base Sn plus 1. So that means log 2 base Sn plus 1 is at least H of k minus n times RL log 2 base P. Okay. So essentially, we have this theorem. If P, C, K, E, D is a crypto system, size of C is same thing as size of P. Keys are chosen, equiprobably. Then RL is the redundancy of the language given a string of ciphertext of length n. The expected number of spurious keys is at least size of K divided by size of P raised to power n times RL minus 1. So this is a result. I mean, this is a kind of bound actually. We can also define unicity of distance. So it's a value of n denoted by n naught at which the expected number of spurious keys becomes 0. So if you set Sn bar is equal to 0 and solve for n, it turns out that n naught is log 2 base size of k divided by RL times log 2 base P. And here is a expression. So if for substitution cipher, size of P is 26, plain text, size of K is factorial 26, key space, right? RL turns out to be 0.75. So N naught turns out to be, we can substitute here in this formula. and not turns out to be this, which is roughly 25. That means given a ciphertext string of length at least 25, a unique decryption is possible. So, so this is the way you understand these results basically. Okay, so I think that's all. So basically, I can summarize what we know. So I hope you have seen the assignment too, right? So you probably start doing some of this stuff. And so I think the classical cryptography thing is done. So basically, what we looked at, couple of probabilistic arguments, right, and entropy business to actually analyze the crypto system, and we looked at some of the classical crypto systems and their analysis. So two chapters are done. Okay. Next is more interesting, which is private key cryptography or symmetric key cryptographies. So private key cryptography means the encryption key and decryption key is same. Okay, the symmetric key cryptography, and then we will look at public key and protocol. So public key cryptography and protocol. So in the private key cryptography, there are plenty of interesting things. So how do we encrypt? So we are going to talk about block cipher. What is block cipher? Sequence of permutation and substitution operations. So there is a plain text. You do sequence of permutation and substitution operations, right? So normally it is iterated cipher, and there are two key components: round functions and key schedule. So I think you must be knowing Lucifer cipher was the first time which was used by IBM, and later on DES was discovered, and in year 2000 we have got AES. Okay, because DES is kind of outdated. So both of these ciphers are dependent on this kind of mechanism. So actually you will see that we will give a full lecture on DES. You will understand how it works and so on. And so so in this iterated cipher, basically encryption, so encryption of a plain text will be through n similar rounds. Okay, and k is a random binary key of some some length, and using k we construct n round keys. So there is a one key which is acting as a seed key, and that gives you bunch of round keys or kind of sub keys. Okay, so using k you can obtain k1, k2, k3, kn. Okay, those are the things. So list of round keys k1, k2, kn is the key schedule. Okay, so key schedule is constructed from k using a fixed public algorithm. So this algorithm is known to everyone, how to construct the key schedule. The round function g take a round key kr and a, so there are two inputs actually, a current state. Okay, round function takes a current state and a random and a round key kr. Okay, so next state is WR, RF state is G. So you can see that G is the function. Two inputs are WR minus 1 and KR. Okay. And the initial state WR is X, which is the plain text. So this is the general outline. How do you look at the block cipher? So basically, you start with a plain text, okay, and then you get the initial state, which is W0, okay. W0 is equal to X, which is the plain text. Next state will be W1, then W2, then W3. So basically, WR is function of WR minus 1 and KR. KR is a key at the RF state. So here is a more precise way how it happens. So the ciphertext Y is the state after all n round. So initially you start with W0, which is the plain text X. W1 is a function of W0 and key K1. W2 is function of W1 state and key K2 and so on. Wn minus 1 is function of Wn minus 2 and key n minus 1. Wn is function of Wn minus 1 and key Kn. So finally, Wn is nothing but our ciphertext. Okay. So essentially, there are a bunch of round keys. From one seed key, you generate a bunch of round keys through some algorithm, which we are going to talk about later on. So this is the key idea about the block cipher. Okay. So there is a key which is acting. So from one seed key, you get different round keys, and each round key is used in each round to give you some jumbled text, from the plain text, and you keep on doing this until you get some final ciphertext. Okay. I mean, designing of these block ciphers is very easy. Analysis is a bit tedious, which I am going to show you. I mean, beautiful, right? So which we will talk about it later on. So for decryption, what you do? G should be injective function. Okay. So that is, we should be able to find G inverse. Okay. So G inverse G W X Y Y should be W, right? So starting from the ciphertext days, you apply the G inverse, you get next round, next round, next round until you find the plain text, which is purely the reverse process. At last, you can do the inverse, right, at each step. So that is a decryption round. Okay. So got the idea? Block cipher consisting of certain blocks, key, round keys. Round keys are generated through some seeds key, right? And I'm just summarizing. This is the process. This is the whole process for encryption. This is the whole process for decryption. Okay. And one popular technique is substitution permutation network, SPN. This is simple iterated cipher. Okay. Okay. So substitution permutation network. So L and M are positive integers. Plain text is a binary vector of length LM. So we are assuming that we are working with binary vectors. Okay. Binary vector of length LM. Ciphertext is also, of length LM. So LM is the block length of the cipher. So there are two components of this algorithm. It's called as S box. So basically pi S and pi P. Let me show you what are these pi S and pi P. Substitution box and permutation. Substitution and permutation. Substitution and permutation. That's what it does all the time. So pi S is taking L bits. So you're right, 0, 1. So binary bits, right? Bits, L bits, and giving you L bits again is a permutation of the 2 raised to L bit strings of length L, right? So just a permutation. Okay. And pi P is a permutation of integers from 1 to LM. So pi P is acting on 1 to LM. Okay. So permutation of these integers, right? So these are the two things. So basically, pi S and pi P are two components. So pi S is used to replace L bits with a different set of L bits. Okay. And pi P is used to permute ln bits by, changing their order. Okay. So this is the two thing. Pi s is used to replace L bits with different sets of L bits. Pi p is used to permute LM bits by changing their order. Okay, so this is substitution and permutation. Substitution and permutation. So given an LM bit binary string, so if x is equal to x1, x2, xLM, I can denote a notation. So I am taking the first L bits, I am denoting by x, and then this is this little bracket x1. Okay. Then I am using this pipe, I mean double pipe. Okay. So the first L bits, then second L bits, and third L bits up to, we have m such things. So each such block. So I can see basically this is the notation for each I. X, this little bracket I is basically xi minus 1 L plus 1 to xil. These are L bits in each such block. Okay, these are the bits now. So SPN will have n rounds. In each round except last round we will perform m substitutions using pi s followed by a permutation using pi p. So prior to each substitution operation, we will incorporate round key. Okay. So by some simple additional operation, we'll perform the round keys. Just adding, okay, the keys at each stage. So here is our crypto system, SPN, substitution permutation network. So L, M, N are positive integers. Pi s is a permutation. Pi p is of course permutation. So that is permutation of bits. This is permutation of those integers. P and C are binary strings of length LM. So plain text and ciphertext are binary strings. Okay, and key is nothing but subset of these things. Okay. Now this consisting of all possible key schedules that can be obtained from initial key using a scheduling algorithm. So this is there are different ways you can generate this scheduling algorithm. We will talk about it in details. So for a key schedule K1, K2, Kn plus 1, so these keys are used at each operation, right? Each round. We encrypt using this algorithm. Okay. Here is one such algorithm. Pseudocode. So X is in what are the inputs? X is the plain text. Pi s and pi p you need to tell what are those things, right? And then key schedule K1, K2, Kn plus 1, right? Okay. So now if you look at the algorithm, obviously initialization is W0 with plain text. Then from 1 to n minus 1, what we are doing, we are adding Kr, right? Here in WR minus 1, right? And then we are applying pi s, and then you see pi p, both of them are used, right? So basically we have so UR is the input to S box in input to S box, and VR is the output of X box in round R. WR is obtained from VR by applying pi p, and then basically, and the key thing is here, round key mixing is happening here. You see, WN minus 1 and XOR of Kn. Okay. So first and last operation SPN are basically, XOR. You see, the last one is with this here, Kn plus 1. Okay, and that is your ciphertext. This is the general layout for the substitution permutation network. But I think, yeah, no, we will not go into this today. This will involve some understanding. Yeah, so I think this example we will do next time. Okay. So I gave you some idea. Next time we will do the example. Okay, so that you understand. We cannot cover it today itself.